All right, for everyone that's watching this video, what the class is working on currently is taking these two functions, m of x and a of x, and identifying, or not necessarily identifying, but first arranging the equation in the standard form, and then identifying the degree, identifying the end behavior, and then determining the maximum number of turning points. So if you're watching this video, I'm going to ask that you hit pause and go ahead and do that for both of these equations. After you unpause it, I will have both those things worked out. And that way we can check and see what you have. So we're going to pause the video, work through that. And that's the first part of what we're doing in class today. Okay, and for everybody watching the video, here are first your equations in standard form. Remember that's you taking all the terms and arranging them so the term with the largest exponent shows up first, and then we just write each term in so that it is decreasing based on the exponent. So largest exponents first, next largest second, so forth, so forth. The degree, remember the degree is the largest exponent in both equation. And then the end behavior, that's dependent on two things. First, it depends on the sign of the leading coefficient. In this case, both leading coefficients are negative. Tell me that the right side is going to be down in both those cases. And then how we determine the left side is based on whether or not our degree is even or odd. Even degrees, both ends go in the same direction. Odd degrees, ends go in opposite directions. And then last thing, max turning points, that is one less than the degree. And it's just the maximum number of turning points. That doesn't necessarily guarantee that we have 10 turning points and 11 turning points, respectively. Okay, hang tight as we will start our next activity here in just a second. All right, so for the next part of class, we're going to work with these three functions, and we're going to identify first, we're going to arrange it in the standard form. So write in standard form, just like we did in the previous problems. Two, identify the degree, or state the degree. Three, determine the end behavior. Four, determine the max number of turning points. And then what we're going to add on to this is identifying the increasing and decreasing intervals. So increasing interval and then decreasing interval. Okay, and I want to go through how we're going to find those increasing or decreasing intervals together. We basically need to see the graph. And eventually we will graph polynomial functions. We haven't gotten that far yet, right? We've only had one day of class. So for now, how we're going to get the graph is we're going to go to Desmos. Okay, so once you get working on this, you're going to go to desmos.com/calculator, and then you're going to plug in this specific equation. After plugging in the specific equation, you're then going to look and try to identify those intervals for where we either increasing and or decreasing. Okay, so for the video portion, you can't see my screen when I do Desmos, so I'm going to pause the video. Okay, so starting with number one, I identified the increasing and decreasing intervals. The one thing that you were left to do is put in standard form, degree, end behavior, and max turning points. So you can check all that. Nothing really odd that we need to pay attention to there. But if there are any values that we disagree with or feel like it should be something different, let me know. And then we'll move on to the next one. Any questions or disagreements here on number one? Okay, let's look at two. And I believe it's going to be the intervals for where we might have some different answers here. So again, you can check your standard form. The degree is 7. And then your end behavior there. Max turning points would be 6. Any questions or disagreements with the first 4 properties there? Okay, now the intervals. And, I will go ahead and pull up the graphs here. So this graph is increasing in the middle. right? So from 0 to 1.714. So it's actually very similar to number 1. And then it's decreasing everywhere else. So decreasing from negative infinity to 0, and then 1.714 to positive infinity. Okay, so again, those intervals for which we're describing are the set of x values. Okay, the y's, we really don't care about the y's when describing increasing or decreasing intervals. It's the fact that the y's are going up or down, again, is what makes that either increase or decrease. Okay, so if I start on the leftmost part of this graph, I'm going down all the way until I get to this low point here. Okay, that's a minimum. And the x-coordinate of that minimum is 0. So it decreases until we get to where x is 0. Then after x is 0, we start to increase again. And it increases all the way up. I know this graph is kind of funky. You had to zoom in and out to really see some of these points here. And it increases until we get to that 1.714. And after that, it continues to decrease again. All right, any questions on that increasing or decreasing interval for number 2? Okay, so then let's just take a look at number 3. You can go ahead and check your standard form, degree of 3, and behavior, right side up, left side down, max turning point 2. This time we are decreasing in the middle of this graph, and we are increasing everywhere else. So negative infinity to negative 2.16, and then 2.16 to positive infinity is where this graph is increasing, and then decreasing in between those two endpoints. So one thing that's nice and kind of consistent with this, right, is once you identify the turning points, those x values should show up in both our increasing or decreasing intervals. So that's just kind of another place of where you can check things to make sure you're describing those intervals correctly. Yeah. That's a 2. Yeah. What does it look like? Nothing, like a 0 kind of with the slash in the middle. Squiggles. That's a 2. Yeah. All right. Any questions here? Anything we want to go over from this? Okay. Go ahead and flip this page over. We're going to skip that table there. And this next problem, we're kind of looking ahead. We're going to, one, I like the word problem aspect, and that's something we need to always continue to work on, is seeing some words and being able to generate an equation and figure out how we can solve this particular problem. This is the place that prompted my pep talk with my other class, okay? This isn't a problem that I expect really any of you to just jump into and figure out right away, okay? All these word problems take time, and they take a willingness to be wrong, okay? So when we go through this, I'm going to set it up. I'm going to ask you to do like 1 or 2 things. I just need you to try, okay? So come up with some sort of guess. This problem reads, write the equation for the volume of a box that has a length that is 5 inches less than its width and height that is 3 inches less than its width. So starting with the equation, okay, there's a lot going on here. And what I always start with is, and we've done this before, what do I know for sure? What I know for sure is that the volume of any box is equal to the length times the width times the height. For me, I like having some sort of picture. It kind of helps maybe shape what I need to do next. So I'm going to draw a 3-dimensional box. Some of you probably pretty good at this. Some of us can be kind of hard. This is like when I was bored in class, when I was your age, I would draw 3-dimensional boxes. So that one stinks. I'm going to restart. I want it to be good. I always like trying to make it like as perfectly square as possible. Okay, and then this dashed. And that line down. Okay, not terrible, not great though. Okay, and then in this box, this would be considered its width, this would be considered its height, this would be considered its length. All right, so one problem that we have And just when we're generating equations, it's really important that we only have two variables. And right now we have four. We have the volume, the length, the width, and the height. Well, we can't really do much with that. If I said graph this equation, length times width times height, that's not even possible. Okay, so really what our main task here is to take this equation of the volume and write it so that we only have two variables. This is where this other piece of information is going to come in handy. So we know that the length is 5 inches less than its width, and the height is 3 inches less than its width. So basically that should prompt us to rewrite what the length is going to equal and what the height is going to equal. And this is where I want you to come up with something. You need to rewrite the length and the height based on what these words are saying. In your groups, take 1 to 2 minutes and come up with a guess. Do not just sit there and put nothing on your paper. Okay, come up with some guess. What are those words saying and how do we translate that to a math equation? Take 1 or 2 minutes, go from there. And here's what you should have came up with. Based on what those words are saying, our length is the width minus 5. The height is the width minus 3. So W minus 5 and W minus 3. And that allows us to now take this equation for the volume and write it so that there are only two variables. One variable still being the volume, V, but then the length and the height have been rewritten using the width. This is so important when writing equations. Okay? Almost every equation that you work with in algebra should have two variables. Until you get to calculus, you start doing things with 3 variables, but that's a ways away from where you all are at. Now, with this being 2 variables, we can graph this equation now. And again, we will do a whole kind of thing on graphing polynomials. So this is kind of looking ahead. So actually how we're going to figure this out is I want us to think back to our quadratics unit, okay, when we were what we were working on right before break. If this was a quadratic equation, which form is this considered to be in? Factored, factored form, yes. When it's in factored form, if I were to set this equal to 0, what do we do next? We factor, set equal to 0. Now what do I do? Charlotte, what are you mumbling? You got it. Somebody help her out. What do we do next? Yes, yes, you had it. Don't be shy. Okay, we take each factor, set them equal to 0, and solve. So when I do that, you get W equals 0, W minus 5 equals 0, W minus 3 equals 0. When I solve for W now, what do those points represent on the graph? What'd you say, Delia? These are our x-intercepts, and we can use that to help us graph. So let's do that. Let's find all the x-intercepts here. Well, we've already got 1, W equals 0. I would add 5 and get W equals 5, so that's another. And I'd add 3 and get W equals 3, that's a third. So this particular graph has 3 x-intercepts. We're going to plot those. So 0, 0, 1, 2, 3, and then 4 and 5. So already for us graphing this function, we have 3 points on our graph. Now, we're just going to come up with a quick sketch. So the last thing that would be really helpful here is for us to figure out the end behaviors. If we know the end behaviors, we can actually come up with the shape of what this graph will look like. I have this equation in factored form. If I'm going to figure out the end behavior, I want to convert that into standard form. How can I accomplish that? How can I take this factored equation and get it into its standard form? See, a lot of you writing, you might have ideas. Somebody share your ideas. How do I go from factored form to standard form? Or another way to think about this, what operation is happening between W and W minus 5 and W minus 3? Jake, what are you signaling? Multiplication. So if I want to go from factored form to standard form, I need to multiply all these terms together. So that's how we're going to be able to get into standard form. Then when it's in standard form, we can figure out what the degree is and the leading coefficient and determine the end behavior. So when I go to standard form, this W is going to distribute, and it will only distribute to one set of parentheses. If you distribute it to both set of parentheses, you're over multiplying. Okay, you're multiplying more than what you need to. So now our volume is equal to W squared minus 5W, and then we got to multiply that times W minus 3. These two terms need to get FOILed, okay? Or you can use, a lot of you use the boxes to multiply those things out. However you do it, I don't care, okay? But regardless, I need to take W squared, multiply it by W, and negative 3. So that's W cubed minus 3W squared. Then I'm going to do the same thing with negative 5W. I'm going to distribute that to everything in the other parentheses. So that's negative 5W squared, and then plus 15W. And the last thing that we would do to get this into its standard form is combine like terms. Let's try that again. So volume equals W cubed. This is minus 8W squared, and then plus 15W. Now that this is in standard form, I can figure out what my leading coefficient is. And when I'm determining that leading coefficient and deciding whether, or using it to help me figure out the end behavior, we just care about the sign of it. The sign of our leading coefficient is positive. In fact, that full leading coefficient is a positive 1. The degree is 3, which we care about it being odd. So the positive leading coefficient tells me that the right side is up. The odd degree tells me that the end's going opposite directions. So if the right side is up, the left side needs to be down. So knowing how this graph ends, I can start to piece together just a quick sketch of this graph. So I'm going to draw on the left side my graph going down. So I draw an arrow. So it's going down if I continue to work left. And what we're going to do is we're going to start at this down left end. And I'm going to go up so that I can pass through this x-intercept. And in order for me to pass through the other x-intercept, we have to have a turning point. So I'm going to go up. I'm going to turn somewhere and pass through that other x-intercept. And in order for me to pass through the other x-intercept, once again, I need to turn. So here's another turning point. And then passing through that x-intercept helps me get my right end to go up, which is exactly what we needed. And this is a quick sketch of what our graph looks like. Could we accurately describe the increasing or decreasing intervals based on what you see here? Nina, you're shaking your head no. Why not? Okay, yeah, we don't have specific points. Which specific points do we need to describe those intervals? To describe the intervals. What points on the graph might I need to describe those intervals? Well, we know that this starts all the way left at negative infinity. So what about this graph that's not accurate does not allow us to describe the intervals? Yeah, Delia. The turning points. We do not know exactly where those turning points are at. Okay, I just estimated. There was no reason for me going up to that particular amount. Okay, or how far over that is. Okay, I am just kind of estimating where that is. So if we want to describe the intervals, we would need to figure out where those maximums and minimums, or thus the turning points, are located at. All right, we are going to stop right there.